Properties of inverse trigonometric ratios. In this module, you will learn about the properties of inverse trigonometric ratios. Recall that if y equals sine inverse x, then x equals sine y. And if x equals sine y, then y equals sine inverse x. This is equivalent to sine of sine inverse of x equals x if x belongs to the closed interval minus 1, 1. Sine inverse of sine of x equals x if x belongs to the closed interval minus pi by 2, pi by 2. Property 1. Let us now prove that sine inverse of 1 by x equals cos x inverse x when x is greater than or equal to 1 or x is less than or equal to minus 1. Let x be greater than or equal to 1 or x be less than or equal to minus 1. Let sine inverse of 1 by x equals y, then 1 by x equals sine y. This implies x equals 1 by sine y. Therefore, x equals cosec y, which implies cosec inverse of x equals y. Therefore, sine inverse of 1 by x equals cos x inverse x. Similarly, we can prove that cos inverse of 1 by x equals sec inverse x when x is greater than or equal to 1 or x is less than or equal to minus 1. Tan inverse of 1 by x equals cot inverse x when x is greater than 0. Property 2. Let us prove that sine inverse of minus x equals minus sine inverse x in the interval minus 1 to 1. Let x be an element in the interval minus 1 to 1. Sine inverse of minus x equals y. Minus x equals sine y. X equals minus sine y. This implies that x equals sine of minus y. Sine of minus theta equals minus sine theta. So, sine inverse of x equals minus y. Therefore, sine inverse of minus x equals minus of sine inverse x. Similarly, we can prove that tan inverse of minus x equals minus of tan inverse x for x element of R. Cosec inverse of minus x equals minus of cosec inverse x for mod of x greater or equal to 1. Property 3. Next we prove that cos inverse of minus x equals pi minus of cos inverse x for x in the closed interval minus 1 and 1. Let x be an element in the interval minus 1 to 1. Cos inverse of minus x equals y. Minus x equals cos y. X equals minus cos y. This implies that x equals cos of pi minus y. Cos of minus theta equals cos of pi minus theta. So, cos inverse of x equals pi minus y. Therefore, cos inverse of minus x equals pi minus of cos inverse x. Similarly, we can prove sec inverse of minus x equals pi minus of sec inverse of x for mod of x greater or equal to 1. Cot inverse of minus x equals pi minus of cot inverse x for x element of R. Property 4. Next property which will be proved is sine inverse of x plus cos inverse of x equals pi by 2 for x in the closed interval minus 1 and 1. Let x be an element in the interval minus 1 to 1. Sine inverse of x equals y. X equals sine y. X equals cos of pi by 2 minus y. This implies that cos inverse of x equals pi by 2 minus y. So, cos inverse of x equals pi by 2 minus sine inverse x. Therefore, cos inverse of x plus sine inverse x equals pi by 2. Similarly, we can prove that tan inverse of x plus cot inverse of x equals pi by 2 for x element of R. Sec inverse of x plus cosec inverse of x equals pi by 2 for mod of greater or equal to 1. Property 5. Next in the series, we need to prove that tan inverse x plus tan inverse y equals tan inverse of x plus y within brackets whole divided by 1 minus product of x and y with the condition xy is less than 1. Let xy be less than 1. Let tan inverse x equals theta 1 and tan inverse y equals theta 2. Then, x equals tan theta 1 and y equals tan theta 2. Tan of theta 1 plus theta 2 within brackets equals tan theta 1 plus tan theta 2 in the numerator and 1 minus tan theta 1 and tan theta 2 in the denominator. Replacing tan theta 1 by x and tan theta 2 by y, we get tan of theta 1 plus theta 2 within brackets equals x plus y in the numerator and 1 minus xy in the denominator. This can be written as theta 1 plus theta 2 equals tan inverse of x plus y in the numerator and 1 minus xy in the denominator. Therefore, tan inverse x plus tan inverse y equals tan inverse of x plus y within brackets whole divided by 1 minus product of x and y. Similarly, we can prove that tan inverse x minus tan inverse y equals tan inverse of x minus y within brackets whole divided by 1 plus product of x and y with the condition xy is greater than 1. Property 6. Lastly, we need to prove that 2 tan inverse x equals sine inverse of 2x in the numerator and 1 plus x square in the denominator with the condition mod x is less than or equal to 1. Let mod x be less than or equal to 1. Let tan inverse x equals y, then x equals tan y. On substituting x equals tan y on the right hand side of the equation, we get sine inverse of a fraction with numerator 2 tan y and denominator 1 plus tan square y. This is equivalent to sine inverse of sine 2y. Now sine inverse of sine 2y equals 2y, which in turn equals 2 tan inverse x. Hence, we have proved 2 tan inverse x equals sine inverse of 2x in the numerator and 1 plus x square in the denominator with the condition mod x is less or equal to 1. Similarly, we can prove that 2 tan inverse x equals cos inverse of 1 minus x square in the numerator and 1 plus x square in the denominator with the condition x is greater or equal to 0. 2 tan inverse x equals tan inverse of 2x in the numerator and 1 minus x square in the denominator with the condition mod x is less than 1. In this module, we have learnt about the properties of inverse trigonometric ratios.